In this question, we're given a surface that apparently has a local minimum, and a table is even provided with output values for this shape. Now we can scan through the table and just see if we can identify the very lowest height on the whole function. Looks like right here is the one we're looking for. So this function may have a minimum at the coordinates 1, 2. But a table isn't enough for proof. We want to go through the process of setting the partial derivatives equal to 0 and then solving for the location where there would be a critical point. Alright, so I'm going to put 1, 2 appears to be the minimum value. Now let's find the partial derivatives of the function. I'll differentiate with respect to x, pretending like y is just a number. So we'll get 2x minus 2 for that. Now let's find the partial with respect to y. We'll get 2y minus 4. Okay, our next job is to set the partials both equal to 0. And this is an AND type of situation. It's not an OR. Both of these conditions have to be true in order for us to find that horizontal tangent plane. So let's see if we can solve here. All right. Our solution agrees with what we see in the table. So there is a critical point at 1, 2. And we can look at the table and see that this would be a minimum value because all the other values of z around that point are larger than the value at that point.